Hello.
So
Ah,
everyone everyone else except Johanna, we can maybe mute our microphone and we can uh, open it when we want to ask something. And this is the sixth emanate. Johanna will present life cycle analysis of second generation biofuels. And let's give it to Johanna.
okay, thank you. Well, and first, I'm happy for presenting today and having an audience of people interested in this topic. Yes, I will be presenting on life cycle analysis of second generation biofuel, in particular ethanol, produced from sugarcane bagasse. So for those who are not so familiar with the biofuel language, the first generations are usually those fuels that come directly from sugar, like from sugar cane or corn, like from the immediate starch or sugar that will produce the ethanol. But the second generations are those that are produced from lignocellulose or from agricultural wastes. Okay, so the interest of studying this type of biofuels revolves around the idea that for the first generations there are concerns about competing with food crops, competing for the soil, for the labor, for the production itself of these vegetables, or let's say that this biomass, instead of for feeding the people, but for doing fuel. Okay, so there is like a polemic there, and that's why the second generation biofuels are usually better in terms of overall impact, because they don't compete with the food. It's just an agro-industrial residue or agricultural residue that can be further used to produce something of value. Okay, so the interesting thing about this presentation is like we are going to be talking about the life cycle analysis as a methodology for understanding the environmental impacts of whatever product humankind produces. But I will present it in a very practical way, because you are going to be able to understand the methodology as as I was developing the study. Okay, so a little bit of how I arranged this presentation. Okay, I'm doing the introduction, then I'm going to present you the goal and the scope of the study, then an inventory analysis, or also called life cycle inventory, the impact assessment of those effects that the production of the biofuel has on the environment. So there is a life cycle impact assessment on these impacts, just to mention, and then the interpretation. I also wanted to say that I developed this study in the CIEMAT, which is the Energy, Environment, and Technology Research Center, CIEMAT, placed here in Madrid. It is part of the Ministry of Science, Innovation, and Universities of the Spanish government, and it has 5 divisions where they basically do research on energy, environment. There is a national fusion lab there, and also some technology research and basic research. And within the energy department, there was an energy system unit, and that's where I did this work. And so for those that are not so familiar with the life cycle assessment and what it is, I will put it like very simple. It goes from the concept that every product or even service that we use in our daily lives comes from a chain of processes that go before that or upstream of that product. And then after we use it, then that product goes somewhere, usually, okay, to the garbage. We have the recycling policies and everything, but usually it has an end of its life, right? And it all starts with raw materials from nature. Generally, even more elaborated raw materials, they all come from basically from the nature. And if you see the entire cycle, there are a lot of things going on in each one of these stages. And this assessment that is basically concerned about how the overall picture looks like, and what are really the impacts of each and every input or each and every ingredient or material that you use to make your product, and then how it impacts when its life has ended and you just discard the product. Okay, so I just want to make a little bit of context as well as of the technique, like how it evolved, and how it is what is now. I thought initially when I started studying this topic that it was something very recent, but actually it goes back to like 1960s, where some studies were started to be done to understand the energy consumption and resource consumption of um, of many products have been manufactured. And then in the 70s, there was an like the father of the LCA is a French British environmentalist. Last name, go look for him, and he did a book with together with other 30 scientists called A Blueprint for Survival. And their main concern was about the growing population, the growing demand of finite resources. So they wanted to understand, like, okay, if people start consuming more and being more people in the planet, like our resources are going to suffice, are going to sustain this. And with that question in mind, a lot of people or representatives of many industries and governments started to look at this as a problem. Okay, so in the 70s in the United States, the Coca-Cola company made some analysis, also taking into account the economic part, of course. Then in the 70s, 80s, many studies were carried on in the United States and also in Europe, but with a very informal framework, let's say. It was mostly considering and assuming certain things regarding each one of these companies. And then in the 90s, they started, like the community started understanding that there was a need to really create a framework and standardize it. And in that sense, the United Nations Environmental Program created an initiative to organize all this information and all these methods. And that was how the methodology itself, as we know it now, was born, let's say, like in 2002, around that time. And later on, it was also made an ISO. So now we have these two ISO standards that, let's say, frame everything that you have to take into account. You can also look for this later. So you better know the concepts and more or less how is the analysis done. And so, okay, maybe you have heard about the term cradle to grave or cradle to cradle. These are type of LCAs that take into account, okay, the origin of the product and then the end use. Or cradle to cradle when they, let's say, make it more circular, and they say, okay, what happens if we, let's say, recycle or reuse most of the components of this product. Another important thing is that the LCA is mostly done on consumer products. I mean, it's very weird to find an LCA on other type of like upstream materials or components. Maybe you have heard about carbon footprint or water footprint, but these ones are also LCAs. The only thing is like they are focused on the carbon emission of the entire life cycle or the water consumption of the entire life cycle, but they are life cycle analysis as well. This is a process that is heavily data driven. So you need to have a lot of information, and that's also one of the constraints of this analysis in order for that to make sense. And then you will see it as I explain. Then there is also sometimes a confusion between life cycle assessment, life cycle inventory analysis. And the thing is, like, the entire study is called life cycle assessment, and it is made up of these other two terms. Life cycle inventory is just accounting for how many gallons of water do I need to produce one bottle of bottled water. water, for instance, with the water inside, let's say. And the life cycle inventory analysis is when you, okay, you say, let's say for me to have a gallon of water, then I need whatever amount of energy from the pump that we pump the water. And then that energy that is used by the pump, it needs a fuel, for instance. So those fuels, when you use it and when you pull from the grid, you will, let's say, emit certain greenhouse gases, for instance. So that type of the inventory analysis is what is done in the third term that I'm showing here. And finally, yes, LCA is what we make of it, because it is there are a lot of assumptions. You are the one that is responsible to make the limits or the borders of the systems that you're going to study, and also like the depth of what you're going to study as well. So in that sense, this type of assumptions and this type of yes, preliminary definitions are super important, because at the end, LCA is a tool for making choices or making decisions, informed decisions based on data. And if you want to study an option of doing something A and doing something B, you need to analyze them from the same perspective with the same assumptions, so you can really have an accurate analysis and a good decision. Okay. So nowadays, mostly the LCAs is done in manufacturing and also construction. And another heavy user of this type of analysis are academia and consulting, as well as government. So the methodology is summarized in this picture. So we first develop some goals of our study and the scope. Again, in the scope, as I was mentioning, you are supposed to set the borders, like the limits of your study. Then you make the inventory analysis, which is based on the components that make each one of the subcomponents of your system. You make the inventory of the different materials or energy that is used to manufacture that. Then you make the impact assessment, and finally the interpretation. And you see all these arrows going here and there. And the thing is, like, okay, you may start with a goal and with a scope, but as you go and as you start to gather all the information, you may start finding that you have some, let's say, holes in your data, and you may need to revise your goals and scope, because at the end of the day, you want to give a life cycle analysis, but sometimes getting certain information can be so difficult or so expensive or so unpractical that at the end of the day, you need to reframe everything that you are doing as you go, basically. So for this study, I'm going more to the practical side for the second generation biofuel. The goal of this study was to compare the environmental impact associated to the production and use of lignocellulosic ethanol or second generation ethanol and gasolines as fuel for road transportation in Colombia. Okay. Again, I framed this study for comparing the ethanol and the second generation ethanol with the common or the base case, which is gasoline. And this will give us somehow a reference of what is actually happening, because just knowing the impact of the lignocellulosic ethanol by itself, it doesn't give us too much information. But when we compare it with the gasoline, then we say, oh, okay, this is better, for instance. So the scope. A term that is very important to define here is the function of the product. Let's say your cell phone. So maybe the communication device. Okay, that's the function. Communicate. In this case, the ethanol is a road transportation fuel. Okay, we define it is a fuel, but it might be for maritime, for sea, or for the air. Okay, we define that is road transport. Okay, then we define a functional unit. And we say, okay, this can be 1 liter of ethanol. But then, would that make sense to compare 1 liter of ethanol with 1 liter of gasoline? No, because at the end, maybe 1 liter of ethanol is like 70% of the movement that you can make with 1 liter of gasoline. So in order to be again consistent, we have to say, okay, the functional unit will be 1 kilometer of distance traveled, and then I'm going to, because at the end is what we as users is what we do. We don't usually measure. Oh, I'm going to use 5 liters of fuel. No, you say I want to go there. That is 20 kilometers away. Okay. So your functional unit is also something that you have to define, but you have to define it in a, let's say, a smart way and that makes sense. Okay. So I define 1 kilometer of distance travel. And then we have a reference flow, which is like the final product made it, right? In this case, it's ethanol or gasoline. So my flow is the volume of ethanol and gasoline or gasoline required to travel a distance of 1 kilometer. And then I define it a little bit more with a passenger vehicle, because I can say that also with a large truck and it wouldn't make sense. It will have a type of vehicle. Then we have to define the system boundaries. In the case of the ethanol, my system included the crop and like all the agricultural part of growing the sugarcane. Then the second picture here is the processing, like really producing the bioethanol. Then transporting to, let's say, a gas station or a fuel station, and then using it to run that kilometer of distance. So we have certain material and energy coming into this system, and then some material and energy going out of this system. And same thing, I try to draw a parallel with the gasoline. So the gasoline has all the oil production, and then the refining, then producing the gasoline, and then transporting, and then using it as a fuel. Would this be a nice way to do it? Like if I say only gasoline production and distribution and then use, I think it's not fair. I think we have to cover, like when you compare systems, you have to cover most of more or less the same phases or the same stages. So then we have to define the impact categories. So this is like, okay, we're going to study this. If I want to study how much water does it use, then I can say an LCA called water footprint, okay? But depending on what you want to study, you can define several impact categories. So I just made an example here about like energy consumption, climate change, acidification, ozone depletion. So those are like different categories that your product or your process can have. And on the column, I have some names of corporations and more or less which are the type of impact categories that these corporations tend to analyze and study and keep track of. In my case, for this, and mainly trying to comply with the Directive 2009 of the European Parliament in terms of the renewable fuels and energies, they are concerned about two impacts, which is climate change and the fossil fuel use. There is a characterization factor which is more, let's say, okay, the impact is climate change, but I need like a number or something that I can quantify this. So we have a global warming potential, and in the case of the fossil fuel, we have the non-renewable fossil fuel usage. Then there is the category indicator, which basically says, okay, for the global warming potential of this process, it will be, I mean, we'll have certain units, which is kilograms of CO2 equivalent per functional unit. And in order to establish all these, I use the method of environment product declaration, which is more or less like something like a label that you're supposed to have in your products, and they have all these. I mean, they have like a list of all these: the impact categories, the characterization factors, and the category indicators. Okay, so now for my scope, for all this study that I want to do, considering the boundaries that I mentioned before, in the case of the ethanol, covering the sugarcane farming, the ethanol production, the distribution, the use as a fuel, and the parallel with gasoline. This is what tells me what information do I need to gather. Okay. So for doing this, I mean, for getting all this information, and again, I don't know if you remember this far that this was supposed to be done in Colombia. Okay, that it was a Spanish study, but let's say the location, the final location of the study was in Colombia. So I had the environmental impact assessment of the sugarcane crops in Colombia. And that's something that is very important to mention because not all the agricultural practices and not all the yields of the agricultural side are the same everywhere in the world. So depending on how much water do you need, how much fertilizants you use, etc., then the environmental impact of that activity in that place will have a different dimension, let's say. Then for the processing part, I use the NREL study on the conversion of lignocellulosic biomass to ethanol. Okay, this is again another input that I had because they made a very nice simulation in Aspen Plus. I don't know if it's software, but it's a chemical process simulation software where you can simulate an entire plant and with all the different units and even like wastewater treatment and emission treatment, everything. In this case, these experts in the NREL, they did it for corn straw, which is also an agricultural residue, such as the sugarcane bagasse. So there is a parallelism there, but it's not exactly how I would have liked it, because I would have preferred that this was done from sugarcane bagasse. But again, the raw material is very similar in terms of the macro composition of these agricultural waste is like cellulose, hemicellulose, and lignocellulose. So and water. So it's basically something that you can say, okay, well, this works. But of course, again, all these let's say, all these information that I'm giving you, like, okay, this is very accurate and this is not, is part of the LCA. Like, you have to give this information. So the people that are reading this and analyzing this can make their own judgment about the robustness of the study. Okay. Then I used the SEMA Pro, which was the software that I used to do this. And well, I was also considering information sources from the SEMA, which was the place that I used. Okay, so another important thing to start with the scope is the assumptions. So again, as I was mentioning, I will go to the second bullet point and then I will go for the first because the first is a little bit complicated, but okay. I'm making an equivalence between the corn stove and the sugar cane bagasse. So that's something that I'm just making clear from the beginning. Then I'm making also an equivalence between the process simulated in Aspen in the simulator in the computer with a real industrial process. I'm also assuming that the SEMA Pro process that will account all the components which is based in European data, will be equivalent to the process in Latin America. And to make an example of this, let's say I need caustic soda for my process. So I'm saying if I use the SEMA Pro caustic soda, some of them have like a overall composition or overall data behind it from ROW, like rest of the world, and some of them have from the US and for Europe. Okay, but mostly SEMA Pro because it was developed in Netherlands. It has a lot of European data, so I'm assuming that it's the same as it is in Latin America. And then this system, this plant, let's say that I'm simulating through SEMA Pro, has power and steam cogeneration using the sugarcane bagasse and some process waste, some fibers that are remnant residue from the process. And going back to the first bullet point, I just wanted to mention that this term called allocation, which is another term of LCA word. The allocation, let's say, okay, we grow the sugar cane and we grow it to have the sugar cane juice and to produce sugar. That's its main goal. You don't produce a sugar cane for having the bagasse, and you don't produce a sugar cane for producing second generation biofuel with the bagasse. So, like, the idea would be that all the environmental load, all the environmental damage or effect should be accounted for the sugar production, the refined sugar production, because that's a major driver for you to grow the sugar cane. Okay, and the bagasse is more neutral. The bagasse is just something that is there that could be just sitting in the field in the soil, but you are making a
Hello, I think it's mute.
I think I saw that Jean Joseph was muting Johanna.
Oh, j'ai touché. Ah non, c'est bon, c'est rétabli.
Maybe you press something wrong.
Oh, sorry.
Johanna, can you unmute yourself?
Johanna?
Hello?
Just the mute button, yeah.
Go to Hangouts, click on the mute button.
hello.
Yeah, thank you.
Sorry.
Oh, so what was the last thing you heard?
Just that slide, the same slide.
All right. But did you hear about the something?
Yeah.
Okay.
And yeah, you can continue.
All right. So let's say to make it very conservative, you can put 100% of the environmental load of the sugarcane farming to the bagasse. Okay, but to be fair, it should be zero, and you will see later how this goes. Then we go to the inventory analysis, and in this case, again, I show you the same picture. For the crop, I use this study from Colombia. Then for the process, for the process, I use the study by the National Renewable Energy Laboratory, and then for the distribution, because I use that study to know the distance between the sugar crops to the nearest distribution centers of fuels. And then, okay, this is more or less like a flow diagram, and then you see here the handling of the raw feedstock. Then it goes through a process of pretreatment and conditioning. It uses ammonia, steam, acids. It produces some condensates and some effluents that are treated in a wastewater treatment plant. Then all the bagasse that has been pre-treated and conditioned goes to the enzymatic hydrolysis and fermentation. Then you go through a distillation process, and finally you store your product. And some of the solid separations, solids are separated in the say purification process of this ethanol, goes to the boiler, and with that you produce steam and electricity. So I had the flow of the different products, and mainly what is in red is like the product. Okay, it goes feedstock, then it transforms into a hydrolysate, then it goes something is called beer, but it's ethanol, and then once you have your product, you store it. Okay. Oh yeah. you can produce biogas with the wastewater treatment, and then that gas goes to the boiler. Okay, for the raw material production, we have inputs and outputs. We have some inputs like land use, which is considered an input. The CO2 that the plants are consumed while they are growing. And then we have some materials like fertilizers, agrochemicals, fuel, electricity. And then I created an assembly called bagasse, okay? And I say, okay, for 1 kilograms of bagasse, how much of these resources do I need? And how many outputs, how much of air emissions, effluents, and solid waste I will produce? For the ethanol production, it's the same methodology. Okay, I have some inputs and I have some outputs. And then inside the production of ethanol, I define four assemblies. Sorry for if the word assembly is a little bit weird for these type of things, but remember that LCA is also for like pieces for making a product. Let's say all the pieces of a cell phone. So these are type of assemblies, but in this case, it's not something like that, but it's like a fluid, okay, or a stream of products. But it is also assumed by CIMA Pro as an assembly. So I define the hydrolysate as one assembly, and then the enzyme production, and then the beer production, and then the ethanol production. And for the ethanol distribution, same thing. You may need gasoline to. Oh, I didn't translate that part. Gasoline, it says gasoline to have your trucks transporting your fuel from your plant to the distribution center, for instance, and of course the transport of 1 kilogram of ethanol, like very pure ethanol, anhydrous ethanol, to the station. And finally, the ethanol use, which is, as I mentioned at the beginning of the presentation, 1 kilometer of travel. So yeah, I don't want to confuse you with this, but this is basically just for you to know that I had all this data from the NRELs, like a very well-developed PNID, DFP, with the mass balance down here, and also I used Excel to more or less calculate based on my workflow, which was, let's say, 1 kilogram of the bagasse, and then 1 kilogram of the hydrolysate, of the beer, of each one of these medium products. Okay, so this is a view of how the CIMA Pro screen looks like. Sorry that is in Spanish, but it's basically objective and scope, inventory, impact assessment, interpretation, and some general data. So here is where I created the different assemblies. As I was mentioning, for instance, this bagasse includes everything that you need to make 1 kilogram of bagasse, and that includes everything that is in the agricultural side. Then from the hydrolysate to ethanol is more in the industry. Okay, so with that bagasse I produce a hydrolysate, and then with that hydrolysate some enzymes. Well, I don't say enzymes. Okay, enzymes. I make the beer, and then with the beer I purificate, I distillate, I do some process on it, and then I produce the ethanol. Then I transport to the station, and then I use it. So these are the 7 assemblies that are part of the phases of this product. And then I decided to analyze the life cycle from 2 perspectives. Only until the production, like all the agriculture, until the industry part, and then covering the distribution plus usage. So this is also a view for you to more or less be familiar on how it looks. You can put pictures like saying something, okay, this is a beer. And then here is where you put the quantities, as I was mentioning, from the mass balance. So let's say my assembly here is the beer. Okay, so all these quantities are for making 1 kilogram of beer. Okay. And then this other process is the sugar cane. So I say, well, for 1 kilogram of sugar cane, at the farm, how many inputs do I need? Like energy, transformation of the land, etc., the water from the river, blah, blah, blah. All this data is embedded in the CIMAPRO. Here it was the allocation percentage that I mentioned, that this could be like really could be zero, because I'm not studying the sugarcane production for the sugar, but it's just a residue. I just made it 100% to make it like super conservative, and to cover like any change of regulation that they say, no, now the residues, they have to have full allocation, let's say. Okay, so the life cycle for production of 1 kilogram of ethanol covered these two stages. And for the, as I was mentioning, for covering the 1 kilometer of distance, I mentioned that was called the life cycle of the ethanol use. That was only like a extra explanation of the situation. Okay, I jumped a little bit on the explanation, but okay, that was what I was just said before, that I made two cycle analysis in that sense. Okay, so for the ethanol fuel, which includes only the part of farming and industry, I say, okay, for one part of ethanol, what do I need? And in this sense, this is the result. This is more or less, okay, what is the air emission, what is the wastewater, and what's the electricity that you can produce from the remaining sugarcane bagasse. This is just a little bit of the explanation of the utilities that were around this facility. For the wastewater treatment plant, there were some chemicals added to this used water, and it produced several streams of products. Same with the boiler and the generator. And also, again, something that is very important about the context. For instance, in Colombia, around 80% of the electricity is produced with hydroelectric power. So when you want to take into account how much am I reducing from as an emission, for instance, as a GHG emission, for instance, when I use my own bagasse to produce this electricity, or my own subproducts to produce this electricity. It's not the same as in an electric mix that is fully fossil, for instance. It will have a larger impact if it is a fossil fuel type of mix. But if it is it has a lot of green energy, then the impact of reducing that electricity consumption from the grid is not so large. So the life cycle impact assessment then assigns the life cycle inventory. So all these quantification that we did before, then we have to assign these quantities or these effects to certain impact categories, as I mentioned before, the climate change and the non-renewable energy use. So for each impact category, an indicator is selected, as I mentioned before, and all these all this collection of indicators is then what really provides the information of the environmental issues that are related to the inputs and the outputs of this system. For instance, so these are mandatory elements of the methodology, which is like selecting the impact categories, assigning the LCA results, or which is the classification of all this data that you gathered, and then calculating some indicators. The category indicators were the global warming potential in kilograms of CO2 equivalent, and the non-renewable fossil fuel use. And this is done automatically backstage by CIMAPRO. So you don't need to learn about all these things. You just need to click which type of impact category do you want. And the CIMAPRO has embedded all the information that is behind the scenes, and it will just give you the information. It gives you some tables, but also some plots. And for instance, here you can readily see that the ethanol production, ethanol use, has the largest contribution to the environmental impact of the ethanol as fuel. Then for treating the wastewater and yeah, reducing the contaminants of this water before putting them in the water bodies of the nature, you need to treat it. But it also demands certain chemicals to, like sodium hydroxide. So this sodium hydroxide, for instance, it carries some environmental impact just for producing the sodium hydroxide. So that this is how this middle section here is produced. And then for the electricity, as I was mentioning, okay, so you produce your own electricity, and that's a green. That's something that is minus. Okay, it's minus because it mitigates the CO2 that otherwise would be produced through an electricity mix that, even though is very green, is not fully green. So my results were that for each kilometer, for instance, of ethanol, for each kilometer of driving made with the ethanol, it will produce 0.109 kgs of CO2. And for the same trajectory, it will need 1.300 megajoules or equivalent. Okay, so yeah, I will go back to this table again. So just for you to have an idea, the global warming potential of the entire cycle, a lot of things have to do with the bagasse. That's why I think it is important that you define the allocation. If I were to say, okay, the bagasse is 0, then this distribution will be totally different. And also this leads us to know that the fact that the bagasse is a waste, and it shouldn't be accounted for this global assessment, then it makes like 60% of the impact. So if we forget about it, then the numbers will be even better. And for regarding the non-renewable fossil fuel use in the different stages, mainly is the wastewater treatment and also the beer process, because it demands a lot of energy and also heat. And so to put it in context with the gasoline, we have that gasoline to just run, like, let's say 1 kilometer, it uses almost twice. Generates almost twice the effect of the second generation ethanol. And this third column here is a referential study that also was done for the bioethanol, and the numbers are a little bit different. Basically, because I went to a very large detail in this analysis, so that's mainly the reason. And yeah, to clarify more, like the reduction that you can have in terms of global warming and non-renewable fossil fuel use could be around like 60% in the case of the non-renewable fossil fuel, and almost 50% for the global warming potential. So the decision would be, okay, the second generation ethanol, even though we are allocating 100% of the impact of the bagasse to this product, even though it is a good decision. This is more or less like graphically, you can see the 50% reduction. And okay, well, these were my conclusions, where I just mentioned about what was the global warming potential and the use of energy for 1 kilometer drive for this using this biofuel in Colombia, which are the largest stages that produce the largest impacts, which are the raw material production, the wastewater treatment, and the distribution. Of course, the distribution was assumed to be done with gasoline. From that, you can draw also another interpretation, which is okay, changing the agricultural practices and the wastewater treatment process or technology could improve to a better performance of these in terms of environment of this process. And well, just the conclusions that I just mentioned in the last table. And some of the limitations, as I was discussing throughout the presentation, was like, okay, I had data from a robust process simulation, but still it's not a real operating process. It still is not a commercial scale process. So there might be changes and some differences when you do it in a, like if you gather the data from an operating and running plant. For the the processes of fermentation, hydrolysis, etc., are not super easy to model in Aspen. Aspen is more for petrochemical and refining type of process, but still, I mean, it was they made a good analysis for this data. And also what I was mentioning at the beginning, if the raw material wasn't cornstalk, but it was bagasse, then it could be like even more certain, the results that we can get out of this. Okay, then I made some recommendations to the system energy system unit in Emanate back then about like we can now, because the lignocellulosic bagasse ethanol is already commercial, so there is opportunity to get data from an actual process. Also about the allocation of the environmental loads, either 0%, 50%, 25%, or 100% to the bagasse or not. And then, of course, I made all these analyses more or less framed in the European regulations and European perspective. But as this has been evolving in Colombia, then we have to also analyze maybe other impact categories that the Colombian regulation may want to know, like acidification of soil and other type of impacts. And that's it. Thank you.
Hi, thank you. Congratulations. It's a very well research and also very well presentation from you. I believe we are here to learn. So anyone that wants to ask Johanna, this is the time. Anyone from Hangout first?
Yes, I have question. This is Astu here.
Okay.
Yeah. So, did you take into account, like during your analysis, for example, if you're using just gasoline and you're not using the ethanol from the biogas, so what are the normal process that you would do to the waste of the sugarcane? And that normal process, I don't know, probably incineration, probably. So that process will also emit some CO2, right? So with the fact that you are actually transforming that sugarcane residue to an ethanol, it means you're avoiding that process. Is that also something that you take into account? You know what I mean?
Yes. And I think yes, because I mean the way CIMA Pro is set, you will have to, for instance, you will have to make like another assembly where you say, I would incinerate this and produce these gases, and now that is not happening, but this is happening. You will have to tell CIMA Pro to make that assumption.
Okay, and you program that in CIMA Pro?
No, I didn't.
Okay.
So I just got like, okay, there is an environmental impact associated to the sugarcane production, and then I say, okay, all this environmental, I will put it to the bagasse, and then this bagasse I use it to make this product. I'm not concerned about what could otherwise be done. I was concerned about this process in particular. I mean, that was the scope.
Okay. All right.
I know what you mentioned is something like avoided effect.
Yeah. No, I'm just like, if that it means there is also a potential to even save more CO2 if you take that into account on your calculation.
Right.
I think. Uh, no, I think that's my question. I will save it for others if they want to ask question.
Okay, I have question, but I will let maybe John Joseph or Iklima if you have some questions.
Yes. Thank you, Joanna,
Yes.
for this presentation. It was very, very great. I remember for my master thesis, I work on PV project. I made a life cycle analysis of on two rooftop mounted PV systems. Actually, during my presentation, there was one aspect I didn't present, I didn't touch. It was about the life cycle cost, and they asked me some question regarding that during my presentation. I didn't know what to say.
Uh,
Uh, is it something that is really matter today when you, I don't know, when you do the life cycle analysis regarding the methodology? We have the goal, the scope, the inventory analysis, the interpretation. And what about the life cycle cost? Can you say, I don't know if you have some example in some, let's say some case study where where you take into account the life cycle cost.
okay. I would say, I mean, even though it has the name life cycle, and it also calls to the same concept of something that has a beginning and then has several stages until the final end, I wouldn't say it is the exact same type of analysis.
Okay.
Um, and I'm not quite sure about like the capabilities of SIMA Pro to have the economic part associated to this. But I do know that, I mean, life cycle analysis, as I have presented it, is purely environmental. Okay, for the even another aspect that is very and is increasingly being considered is the social aspect,
Okay.
which can be also being studying, okay, what's the social impact in the raw material production, what is the social impact in the manufacturing, what is the social impact in the use, and what is the social impact in the final disposal. And then there is the economic pillar, let's say, of this analysis. But I would say that there are already some methodologies on this, but this doesn't really it's not together with the LCA. So
Okay.
you can have your life cycle analysis of one thing and then study it from different perspectives.
Okay.
The only thing I can say about life cycle cost analysis is that we did some of these in École de Mines in our last semester there, and what it was mainly like the difference between these, it was also like covering all the different stages and all the different costs, but also defined like a horizontal time of life, like life of the project. Let's say something that you will construct and it will last 30 years. So in the life cycle cost analysis, what you will take into account will be all the investment for having that facility built, for instance, or that system constructed or whatever. Then all the maintenance and all the replacements and things that it will need along its life cycle, and then until the very last day of existence of that building or whatever. And this can give you very good information about the overall economy of one option versus another option. Because maybe one option is more expensive to invest, but then in the 20 years of operation, it performs better economically than another that may be cheaper, but then you need over the time of the other one, let's say that lasts 20 years, this one you need to change this every 5 years, and then when you have the overall life cycle cost, then you see, oh no, for the entire span of time, this one is better than this other. So in that sense, it's a little bit different type of study and results.
Okay, thank you, Johanna. Thank you so much.
Yeah, it's actually true what you said. I actually recently read about the life cycle cost. There was, if you're interested in yourself, there is a one paper who was done recently, I think, by someone who's evaluating the options for district heating in Finland. And she or he came up with a very good graph to show the cost of investment and the environmental impact comparison of the four scenarios that they're comparing, you know.
Okay.
So
Uh, but she studied that, or he, using, let's say, those two type of analysis, or like or it was a unique software that gave her.
I don't know.
Okay.
Yeah, I don't know.
I mean, it is possible to study, as I mentioned, like from three perspectives, the same situation, and have these type of results that you mentioned for the paper. I'm not saying that that is not, but I'm just saying that I think Sigma Pro doesn't have the economic part. I think, but I may try to research on that.
Yeah, I was working with OpenLCA, and in OpenLCA, you can put cost in the calculation. So probably with LCA, with OpenLCA, you can do that
Okay,
because
and
there's a
then
column of cost.
yeah, and then there is something like a philosophical question in these type of things, because you don't know how far, like, step behind you can go, because okay, yes, for the ethanol I need caustic soda. Okay, so let's pull all the environmental impact of the caustic soda, but then the caustic soda needs a lot of other ingredients maybe to be produced, and energy streams and a lot of things. So you don't know how far back it goes in terms of this. And same with the social analysis, and same even with the economic analysis. Well, the economic analysis can be a little bit more constrained, but
Yeah,
the social, you never know. There are indirect effects that is very hard to quantify and to really gather.
yeah.
Like that data is super
I
complex.
agree. I agree. I know what you mean. I agree. Yeah.
So the
Okay.
key here for those who wants to work in this or to implement this is, at the end of the day, you need to be very, let's say, smart to focus your borders, your limits of your system, so you don't make yourself like a nightmare trying to gather all the data that you need for everything. So that's one of the, like, practical hints for doing this.
Okay.
Hello,
Ima.
Joanna. Yes,
Hey,
I'm here. Thank you for your presentation. Congratulations for the
thank
project.
you.
So, one thing I found interesting is about the process, the fermentation process or hydrolysis. So it cannot be simulated on Aspen then.
It can be, but
Okay,
are you
because
familiar with the software?
yes, because yeah, I'm just wondering why it cannot be simulated because I mean, you said about that it's hard to simulate or something. Maybe you
Uh,
can
yes,
another.
yeah,
Mm.
because
Yeah.
because these type of processes, like, they are not by
Mhm.
default already defined in Aspen. In Aspen, let's say you can click and put in your layout, you can put a
Mhm.
distillation column. Okay, so it already has
Mhm.
some arrangements inside of that programmatic block. Okay, but for the
Okay.
fermentation, another type of, mainly the bioprocesses. Okay,
Ah.
then
Okay. Yeah.
you have to make the block, and then you have to put like an equation that will simulate the reaction that is going on there, and all the byproducts, etc. So it's a little bit, it's not that it's not possible, but you have to
Mm.
do it.
Yeah, because I've heard once from some colleagues also who's doing work in waste management, and they do the process simulation on Super Pro or Enviro Pro because it's for waste management and yeah, something like similar for biogas
Right.
treatment. Yeah, maybe if yeah, I don't know if it's available there, but supposed to be.
Okay.
Yeah,
Yes,
I mean,
as all the time, you do what you can with the resources you have.
sure. Yeah. And one thing about the cost, because you and Astu also were talking about the avoided costs. So is it possible also to use SIMAPRO to calculate, to estimate like avoided cost through this from the life cycle analysis, or how is it working? How does it work through SIMAPRO?
As I mentioned, I didn't touch the economic part, so I really don't know, and I don't have it like in my personal laptop to open the program and see if it has like a part that has the cost.
Oh, okay.
Now that I'm remembering, I think it has. I think it has.
It
But
has. Okay.
yeah, but I didn't work with that, so I would tell a lie if I tell you exactly how would that work and what type of results you can get. But I guess it's mostly the same as with the environmental results.
Benefit. Yeah.
It will be based on the cost of, let's say, of 1 kg of sugarcane bagasse, and then with that and the cost associated to other streams of that product, I mean, needed for input, then it will give you like the cost of production of 1 kg of beer or hydrolysis, for instance,
Okay.
and then so on, and then you can add up everything and see uh, what is the cost of, or the individual cost of each one of the ingredients or like materials or inputs or whatever, and understand that part as well. It will be interesting to also, because I know that, for instance, if you say, okay, this has a large environmental impact and a large cost, then it will give
Yeah.
you a hint that you have to work in that area, because you can save a lot of environmental damage and you can save a lot of money. Maybe if you improve that. It's
Yeah.
important. Yes.
Yeah, that's true. Okay. Thank
Okay.
you.
But it's
Okay.
usually the opposite. Usually the cheapest things are the ones that are more contaminated. That's why
Yeah.
they keep it like that. It's too expensive to
Yeah.
change,
Yeah.
and then they keep it polluting.
Okay. Okay.
Okay.
Cool.
So I think everyone still has question, but uh, I have several questions that can be the conclusion for this session. So from your perspective, doing this LCA, I don't know like how many months you have to finish this assignment, but what is the trickiest part and what is the like a problem that you encounter from LCA in this assignment, and maybe how can a country like maybe another country that want to do this kind of assignment can do better in maybe collecting data, or maybe another issue that you found can improve the LCA process?
Okay, the ideal world would be like you set your goal and scope, and then you say, I want the data. Like you go to the real places and the real facilities and you gather what you already want. But usually it doesn't work like that. So again, I mean, this is a study that can be done in a great detail or in a medium detail, and there are costs associated to the level of detail that you're gonna have. So it will depend basically on how much, like how much are you able to spend, like let's say like an institution. um, the trickiest part for me is to define the functional unit, or that initial part that I mentioned. Like, okay, from all of that, what at the end of the day will give me like an important information. Because if you don't define this well, then you start like collecting data like a crazy person, and then start analyzing a lot of things, and then it doesn't really lead to anything that is useful at the end. So that initial part is very important. Also, another important moment is when you are trying to gather, as you mentioned, like the quality of the data, to gather all the information that you can. Of course, try to make the most reasonable assumptions, like something that is somehow robust. Like, okay, I don't have this, but I have something that is very similar, and okay, we can go with this because, for instance, we didn't pay for any of these sources of information. But if we were to analyze, maybe as I mentioned one of the last slides, like gathering the information directly from a sugarcane bagasse ethanol facility in Brazil, you can imagine the difference of the cost of that, right? But then also, like, why do you want the study? I mean, if you wanted to, I don't know, pass a policy or something that
Mhm.
will impact the European Union and the world, well, of course, you have to invest a lot. If you just want to, make a study even inside, because I think this is also a tool that can be used for the product and process developers. They can do it like something somehow quick. They can do this, and then they say, well, if we change this and we use this instead of this other material, then what would happen? It's something that can be done like in 2 weeks or something. For this study in particular, I spent 3 months, but like half. I didn't work 8 hours. I was like,
Mm.
I don't know, 4 or 6 hours for 3 months. And also, I was learning about the software. I was learning about LCA. I was learning about all this. But if you are already doing it in a normal basis, I would say like 1 month is for this type of analysis. And for something more simple, like simpler, it could be like 2 weeks.
Okay. I don't know. I just heard about like Google database. They just starting collecting data set of, I don't know how big is now their data set, but yeah, I hope this data can be available in better and more uh, interesting way in the future.
Yeah, and the other challenge that you usually have is like, okay, you have, like, for instance, I had all the streams of, or the mass balance of a plant of whatever amount of liters per day, for instance. But since I was studying a volume flow of 1 liter or 1 kilogram, then I will have to put, I mean, mathematically it's super simple,
Mm-hmm.
but when you have to put all the streams on the base of your workflow, that's the challenge
Yeah.
because it's very tricky. That's a very tricky part.
Okay, that's a very good session we have today. If no one from no one from YouTube has any question, I think so. I hope everyone can have a benefit from this session. And if Astu or Nipu from Emanate has some announcement or information,
No, well, thank you very much for the presentation. It's really interesting, and we will try to find the summary and put it on Facebook. So if you have more questions, also you can put it up on the Facebook comments. No, thank you very much for the.
there's some echo going.
Yeah.
Okay, very good then. From Johanna.
No, just to thank you for hearing me and for your interesting questions. I really enjoyed the discussion after the presentation.
It's true. Okay, so I think that's for today.
Thank you
Uh,
very much, Andre.
Young Joseph, thank you Ima, thank you Astu
Thank
Nipun,
you,
thank you
Andre.
Johanna.
Thank you, Joanna.
Thank you,
Thank
Joanna.
you.